Alrighty, here we go. We are now ready for lesson 18, our last lesson in unit 7. And this is going to be a review of both common multiples and common factors. So we're just going to put everything together today. The first thing I want to talk about is I hope you noticed in your module for this week, we are actually not doing activity 1 today. So I'm going to put a great big X through activity 1. If you did it, if you read through it, you're probably pretty confused. There's no way we can do that in the setting we're in. So we're just going to skip activity 1 and move right on to activity number 2. Okay? In activity number 2, it asks us to solve basically all 3 of these problems in this activity. And so we're just going to work through those. Actually, there's more than 3. There are 4. 5. There's 5 in this activity. So we're going to work our way through all 5 of those problems, just making sure that we understand greatest common factors and least common multiples as we go through these. Okay? So here we go. Number 1. A party. Elena is buying cups and plates for her party. Cups are sold in packs of 8, so that looks like it's an important bit of information. And plates are sold in packs of 6. Another important bit of information. She wants to have the same number of plates and cups. Find a number of plates and cups that meets her requirement. Okay, if we want to have the same number of cups and plates, but they come in different sized packages, then we're going to have to buy more than one package of each in order to get that same number. This sounds to me like because it's getting bigger and bigger and bigger, more and more packages, we're going to need common multiples for this problem. So let's start out by finding all the multiples of 8. And then we're going to need all the multiples of 6. And we're going to stop when we find something that's the same, right? Okay, so the multiples of 8, of course, are 8, 16, 24, 32, 40, 48, 56, 64. Let's stop there and see how much further we have to go. For the multiples of 6, they are 6, 12, 18, 24, 30, 36, 42, 48, 54, and 60. Let's see if we can see did we find any that were the same yet? I think we might have. It seems like I saw, right there, 24. So there's 24. They both have that in common. So that's our LCM. That's our least common multiple. The question asks, find the number of plates and the number of cups that meet her requirement. Well, that requirement would be 24. 24 cups and 24 plates. So that is our least common multiple. Okay, now for part B, it says how many packs of each supply will she need to buy in order to get that number? So in order to get 24 cups, how many packages of cups will she need to buy? Well, cups are sold in packages of 8. So to get 24 cups, I'm going to need 8 times what equals 24? I'm going to need 3 packages of cups. Again, because 8 times 3 is 24. 8 per pack times 3 packs equals 24 cups. Okay, now how many packages am I going to need to get 24 plates? Well, they come in packs of 6. 6 times 4 equals 24. So I'm going to need 4 packages of plates. And if I buy that, then I'll have my same number of plates and cups. Okay? Name 2 other quantities of plates and cups that could get her to meet her requirement. So maybe the 24 isn't enough. Maybe she's got more people coming than 24 to this party. So let's look for the next common multiple. Do we see any more? I see one right here, 48. 48 is the next one. So 48 of each would work. But what if she's got 50 people coming? That's not quite enough, is it? So is there another one? Well, we've run out. right? And there's nothing the same yet. So we're going to have to keep going. So 64, 72, 80, 88. Let's see if that was enough. If I go from 60, that's going to be next is 66. And then 72. Oh, look at that. I think we found it right there. 72 is the next one. So 72 is also a common multiple. So, whoops, what am I writing? So I can also write, or I can also buy 72 of each and have enough for an even larger party. Okay? Again, I could figure out how many packages this would be. How many packages would I need for 48 cups? Well, if the cups are in packs of 8, 8 times 6 is 48. And how many packs of plates would I need? Well, they're in packs of 6, so 6 times 8. So 8 packages of plates. Let's do the same thing for the 72 of each. If I need 72 packages of 72 cups, how many packages? Well, 8 times 9, packages. And to get packages of 6 into 72, that's 12 packages of plates. See how I figured each of those out? And by the way, an easy way to figure out what these numbers are too is to count how many over it took, right? 1, 2, 3, that's 3 packages. 1, 2, 3, 4, that's 4 packages. See how I did that for the first one? 1, 2, 3, 4, 5, 6 packages. 7, 8, 9. Whoops, 7, 8, 9. Oh yeah, that's this one. 9 is this one. And then 1, 2, 3, 4, 5, 6, 7, 8 for the 48. And 9, 10, 11, 12 for the 12. So that's another way. Just count what number that is in our list, and that'll always work. Unless you've missed things. You have to make sure you get every single one of them in the list, and then that trick works. Okay? So that's number 1. Again, in order to solve this problem, we needed to find the LCM. Okay? Let's move on to number 2. Number 2 is all about tiles. It says a restaurant owner is replacing the restaurant's bathroom floor with square tiles. The tiles will be laid side by side to cover the entire bathroom with no gaps, and none of the tiles can be cut. The floor of the rectangle is measured the floor is a rectangle that measures 24 feet by 18 feet. So we're trying to cover a rectangle that is 18 by 24, but we have to use square tiles. So these tiles have to be the same length and the same width. But right now our room isn't the same length and the same width. So I have to figure out what my square tiles length and width would have to be in order to figure out how many tiles I need. The way to do this problem is to find the greatest common factor, because this length and this width is going to be a factor of both 18 and 24, right? It's going to be what number will go into both 18 and 24 but be the same number so that it's a square. Does that make sense? So let's find that GCF of 18 and 24 to figure out the dimensions of my square tile, okay? Just like it says in part A, what is the largest possible tile that she could use? That's the GCF, right? One of the other hints here is that word largest, right? That tells us we need the greatest common factor. So let's start off here by writing some factors of 18 and of 24. Factors of 18 are 1 and 18, 2 and 9, 3 and 6, 4 doesn't go in, 5 doesn't go in, but 6 does, so we are done. Okay? Now for the factors of 24. We know that 1 and 24, 2 and 12, 3 and 8, 4 and 6, 5 doesn't go in, and 6 is already there. So we're done with that one as well. Okay. Now that we have all of our factors listed out, we just need to find the common factors. Of course, 1 is always common, but it doesn't really count. 2 is common, 3 is common. What else is common? Anything else? I don't see anything else in common, so I think 3 is going to be our GCF, right? If our GCF, or greatest common factor, is 3, that means that my square has to have a length of 3 and a width of 3, because 3 will go evenly into this 18, and 3 on this side, or on this side, will go evenly, right, into my 24. So that's what the GCF helps us find, is those dimensions that fit evenly so that we don't have to cut any of these tiles. Okay? So that answers part 1. Explain how you know that it's the largest tile possible. Write the side length in feet. Oh, we should write this as 3 feet by 3 feet to give it a good answer. Explain how we know, because 3 is the GCF. And that's a great reason for that one. Okay? Part B, how many of these largest size tiles are needed? Okay, so if these are 3 inches long, how many of those will I need to make 18 inches? Ooh, this is feet. Oh, shoot, I just caught myself. Oh, no, these are 3 feet. These are 3 feet tiles. This is, I was thinking inches, but no, these are 3 feet. These are 3-foot tiles. So we're still okay. How many 3-foot tiles would it take to make 18 feet? Well, 3 times 6, right? 6 tiles for the width. Well, I'm not writing very good here. Let me try that again. 6 tiles for the width times, right? How many for the length? Well, if this is 3 feet, how many 3 feet go into 24? That's going to be 8 tiles for the length, right? So if I need 6 tiles this way and 8 tiles this way, how many total tiles am I going to need? Well, 6 times 8 equals 48 tiles. And there's my final answer for part B of number 2. I'm going to need 48 of these 3-foot tiles to cover the bathroom. Okay? Name more tile sizes that are whole numbers of feet that could be used to cover the bathroom floor. Well, we found other ones, didn't we? We just picked the largest one. But could I use 2-foot tiles? Yes. Write the side lengths in feet. Okay, so I could have a 2-foot by 2-foot tile. Yeah, I can spell T-I-L-E. There we go. I could also have a 1-foot tile. Now, it's not very common to use that 1, but in this case, a 1-foot tile, 1 foot by 1 foot, absolutely makes sense for this one, doesn't it? So there's my other 2 possibilities. I could use a 2-foot tile and I could use a 1-foot tile. Now, we could go and figure out how many total tiles that would need. It doesn't ask us to do that. If you would like to do that, that's a lovely little bonus you could do, but I'm not going to take the time. Let's move on to number 3. Oh, so just as a recap for number 2, when we were doing this tile problem, the GCF was the way to go on that one. Okay, so that's a good hint for future problems. Okay, number 3 is all about stickers. To celebrate the first day of spring, Lynn is putting stickers on some of the 100 lockers along one side of her middle school's hallway. She puts a skateboard sticker on every 4th locker, starting with locker 4, and a kite sticker on every 5th locker, starting with locker 5. Name 3 lockers that will get both stickers. So this is a pattern, right? Now, the thing about this kind of problem is that, remember, we're putting a sticker on locker 4, on locker 8, and locker 12. Those are multiples, right? Because every 4 lockers will get a sticker. So those are multiples. So to solve this problem, this once again is an LCM problem, okay? I'm going to need to find the multiples of 4 and of 5, right? In order to figure out which locker will get both, right? So let's find the multiples of 4 and let's find the multiples of 5. We need to find 3 lockers that will both get stickers, that will get both stickers. So we actually don't want the least common multiple. We want the first 3. We want more than just the least. Okay, so the multiples of 4 are 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44. I'm going to stop there, see if I need more. We may need to keep going. I don't know. 5, 10. I'm doing the multiples of 5 now. 5, 10, 15, 20, 25, 30, 35, 40, 45. I've kind of matched up now, so let's stop there and see if we need more. We're looking for common multiples here. I see 20 as a common multiple. That looks like our first one, so that's one answer that we're looking for. Are there any more yet? Oh, I see 40. So 40 is another one. Is there any others? Did I skip any? I don't think so. So it looks like we need to keep going, don't we? Because we needed 3 lockers. Then we only have 1, 2. So let's keep going. Multiples of 4. 44, 48, 52, 56, 60, 64. Let's see if that's enough. 45, 50, 55, 60. Oh, and it was. There's my 60. Whoops. And I didn't need to write it again. Maybe I'll just write 65 because we know that's next. So there's my next one. 60 is another common multiple of 4 and 5. So those 3 lockers, locker number 20, locker number 40, and locker number 60, will get both stickers. So lockers 20, 40, and 60 are the answers for number 3, part A. Part B, after Lynn makes her way down the hall, will the 30th locker have no stickers, 1 sticker, or 2 stickers? Explain how you know. So if we're looking for locker number 30, we need to see if 30 is in either of our lists, one list or not the other, or in both. That's basically what it's asking us here, okay? So we need to find the number 30. Let's see if it's in the 4s. 20 and 24, oh, we skipped 30. So it will not get the skateboard sticker, okay? 30 is not a multiple of 4. Is 30 a multiple of 5? Yeah, I think it is. There it is right there. So yes, 30 is a multiple of 5, and the 5 was the kite sticker. So locker 30 will only get a kite sticker because 30 is a multiple of 5, but not of 4. There you go. There's our good reason. See how that works? And you could word that however you want. You don't have to have exactly my words. But if you mean the same thing, then you know you got it right. Okay? Good job, good job. That is number 3. We are now ready for number 4. Number 4 is all about kits. Let's see what this is about. The school nurse is assembling first aid kits. Oh, that's what it means. First aid kits for the teachers. She has 75 bandages, 90 throat lozenges, and all the kits must have the same number of each supply. All the supplies must be used. Okay, so for part A, what is the largest number of kits the nurse can make? Does anybody have a guess? Is this going to be a least common multiple problem or a greatest common factor problem? There's a big hint in this that says largest. When they put the words like largest in there, we know it's going to be the greatest common factor. Another way we know this is that we know that she has a limited amount of supplies. right? This can't keep getting bigger and bigger and bigger like multiples do. We have a limited number of supplies. So we have to stay within those limits, which means we have to do the factors of those limits instead of the multiples of those limits, okay? So let's find the factors of 75 and of 90. All right, here we go. Factors of 75. This is when that multiplication chart will be super handy. In fact, mine is right over here on the other side of the table, so I'm going to grab mine real fast and see if I can use it to help me. Here it is right here. If you didn't print this out the other day, go back to that lesson, the LCM lesson, and print that out because it is super handy. Okay. So let's see here. Basically on our chart here, we're looking for the number 75, right? We're looking for numbers that multiply up to 75. 1 times 75 we know is already 1, isn't it? Okay. Does 2 go into 75? No, we know it doesn't because 5 isn't even. Okay. How about 3? Let's look down the 3 column and see if we see a 75. Does anybody see a 75? Well, it only goes to 45, right? 3 times 15 is 45. But I think we just ran out, right? Let's try, I think 3 will work. Can anybody think of how many times 3 will go into 75? I'm thinking of quarters here because I know 3 quarters, 3 25-cent pieces equal 75 cents. So that's the next one. How about 4? Does 4 go into 75? Well, 4 goes into 7 once, and left over is 3, so that would be 35. Does 4 go into 35? Nope, so 4 does not go in there, but 5 does because it ends in a 5. So how many times does 5 go into 75? Well, this is a chance to use our 5 column here. Do we see a 75 in this? Yep, there it is right there. 15 times 5 equals 75. So 5 and 15. Okay. Next is 6. Does 6 go into 75? Let's see. Let's follow the 6s and see if we get a 75. There's a 72 and a 78, but it skips 75. So nope, 6 doesn't go in. Does 7? There's 70 and there's 77, but not 75. So nope. How about 8? There's 72 and 80, but not a 75. How about 9? Oh, I skipped over. No, there's no 75 in the 9s. No 75 in the 10s. How about the 11s? Is there a 75 in the 11s? Nope. How about a 75 in the 12s? Nope. 75 in the 13s? Nope. How about in the 14s? Nope. The 15s? Yes, there is, but look at that. We've already done that one. Sorry, I don't know if that's on your screen. 75 or 15 times 5 we've already got, don't we? So I think we're done. 1, 3, 5, 15, 25, and 75. In fact, I'm going to scoot these over. Whoops. 15, 25, and 75. Those are my factors of 75. Now we have to do the same kind of thing with 90. 1 and 90, of course. 2, yep, it's even, so 2 goes into 9 4 times. And then that is with a remainder of 10. So 2 goes into 10 5 times, so it must be 45. Okay, 2 times 45, yep, is 90. How about 3? Yes, 3 goes in 30 times. How about 4? Well, we can do some little simple division over here. 4 goes into 9 twice, right? So I'm just going to write the 2 down. That would be a remainder of 1. But does 4 go into 10? Nope. So 4 does not go evenly into 90. How about 5? Yeah, we know 5 will because it ends in a 0. Let's see here. Does the 5 go up to 90? It doesn't quite yet. I was just looking at it. It doesn't quite go to 90. 6 goes to 90 though. 6 times 15 is 90. So do you think 5 goes into 90? I bet it does. We just need to figure out how many times. Well, 5 goes into 9 once with a remainder of 4. 5 goes into 40 8 times. So I think it's 18. So 5, I got off here. Okay, so 5 times 18 is 90. And then 6, when I was looking at the 5s, I noticed the 6 has a 90. 6 times 15. So that's our last number in our list because we've tried them all now. Okay? So there's our common factors of 75 and 90. So how many kits can she make? What are my common numbers here? Well, she can make, of course, 1 kit. She can make 3 kits. She can make 5 kits. Any other numbers that are the same? Oh, she can make 15 kits. Anything else? 25 and 75 do not go, yep, so that's it. So what is the largest number of kits she can make? 15. She can make 15 kits. How many bandages and lozenges will be in each kit? Well, okay, if I make 15 kits, 15 times what equals 75? Or in other words, how many, oh my goodness, my nose itches. Sorry, I had to stop and itch my nose. 15 times what equals 75? Well, we can use our trusty thing here. 15 times 5. 5. So each kit is going to get 5 bandages. And how many 15s are in 90? Well, let's find our 15 and 90, and that was 6. See that? 15 times 6 is 90. So we're going to have 5 bandages and 6 lozenges. And I need to know how to spell this. Lozenges. 6 lozenges. There's our answer for part B. Okay? Very, very good. Again, this was a great example of using the GCF to solve because I was limited by how many supplies I had, so I knew I had to do factors, not multiples. Okay? Last one, number 5. We're getting so good at making these decisions now, aren't we? It says, what kind of mathematical work was involved in each of the previous problems? Oh, now here we go. Put a check mark to show what questions were about. Okay, the party question. Let's bring these papers back out here. The party question. Did we find multiples? Did we find multiples in this problem? Yes, we did. So we're going to put a check mark there. Did we find the least common multiple? Yeah, we did. That 24 answered that first question, didn't it? Right? So yes, we found a least common multiple in that one. Did we have to find factors in the party problem? Well, kind of, because I had to figure out how many packages, right? And 3 and 4 are factors of 24. So yes, we found factors. My dog, I swear. I think it's the mailman again. We had to find factors, but did we have to find the greatest common factor? No, not really, right? We just used factors to help us answer one of our questions, right? Okay, let's move on to the tile problem. Tile problem was number 2. Did we have to find multiples in the tile problem? Well, I don't think so. We had to find the GCF, which means we had to find factors. But for any of these, did we have to find multiples? I don't think so. I think everything here was factors, again, because we were limited by our space on our rectangular floor, right? So I don't think we needed multiples at all, but we definitely needed factors and the greatest common factor, didn't we? Awesome. Number 3 is about the stickers. Okay, so here, back to our stickers problem here. We kind of know what this is going to look for. Do we need multiples or factors or one of both? Whatever. Let's look. Well, we used the LCM to solve this, didn't we? We needed multiples to find these 3 answers, didn't we? So we know for sure we had to find multiples in the stickers. We did end up needing the least common multiple, didn't we, to answer that first question. So yeah, we found the least common multiple. Did we use factors at all? Well, we kind of did on this one as well. Because in order to answer this question B, right, to figure out if 30 was could be one of the lockers that got a sticker, that's a factor of our numbers here. So yeah, we actually did find factors, but we didn't find the greatest common factor. Are we kind of finding a pattern here? How about the kits problem, the first aid kits problem? Did we find multiples in this one? I don't think so. We didn't really, because we had to find the GCF. So GCF was a definite yes. Finding the factors in order to find the greatest common factors is a definite yes. But I don't think we needed to find common multiples at all for that problem. Awesome. So now our table is all filled out. Let's notice the patterns here. The party and the stickers, when we were limited by our supplies, right? When we were trying to figure out how many we could use, that's when we were doing multiples, right? Stickers on the lockers, we were doing multiple lockers. It kept going and going and going all the way down the hallway. Same with the party. We could just keep buying more and more cups and plates, right? So that's when we used multiples, which forced us, in order to answer some of the questions, we had to find some factors as well. But we didn't actually have to find the GCF in both of those. But notice the tiles and the kits, this is when we were limited on supplies, right? That room was only so big. And we only had so many supplies to use in our kits, right? So those limitations meant we never had to do multiples. We only had to find factors and greatest common factors for those. So that's a great chart to help us make those decisions about which method to use, GCF or LCM. I hope that helps you for your homework and your quiz tonight, okay? Of course, are you ready for more is optional. This is a fun one, trying to figure out how these dots move around. Anyway, this is a really fun one, but it is a little bit longer than some of the ones we've seen. So honor students, I'd love you to try that. Next activity is activity number 3, more factors and multiples. Okay, so on these ones, it says, here are 5 more problems. Read and discuss each one with your group, but without solving. So we actually do not have to solve these problems. We are just predicting whether these problems involve finding common multiples, finding common factors, and then we're supposed to circle whatever we think, right? Okay. So again, we're not solving these. We're just taking what we learned from these examples, right? And from this table, and trying to decide which method would we use to solve this. Number 1, for soccer. Diego and Andre are both in a summer soccer league. During the month of August, Diego has a game every 3rd day, starting August 3rd, and Andre has a game every 4th day, starting August 4th. This sounds a lot like the stickers locker problem, doesn't it? Every 4th locker, every 5th locker. Remember that from over here with the lockers? It was actually on the previous page here. The locker problem. Where's the locker problem? I lost my locker page. Oh, it's right here. Remember that locker problem? Where is it? Yeah, stickers on the lockers. This is it. That's what it looks like to me. So I'm guessing it's LCM. So I'm going to say least common multiple. Well, in order to find the least common multiple, we have to find all the common multiples, don't we? Do we need factors to answer this question? What is the first day the boys will have a game? Well, that's the least common multiple. How many of their games fall on the same date? Ooh, how many of them? That's actually going to be common multiples. Do I need factors at all for that? I don't think so. I think we're done with number 1. I think we need the least common multiple to answer this one and all the common multiples to answer this one, right? So I think we're done with number 1. Number 2, performances. During a performing arts festival, students from elementary and middle schools will be grouped together for various performances. There are 32 elementary students and 40 middle school students. The arts director wants identical groups for their performances, with students from both schools in each group. Each student can be part of only one group. Okay, so let's think about this one. Are we going to use multiples or common factors to answer this question? Name all the possible groupings. Well, we only have so many kids, right? So I can't keep multiplying these and get more and more kids in my group. That wouldn't make sense. So I think multiples are actually out, which means, yep, common factors. To name all possible groupings, that's just all the common factors, isn't it? Let's look at part B on this question, see if what else we might need. For part B, it says, what is the largest, there's a hint, largest number of groups that can be formed? That would be the greatest common factor, wouldn't it? Again, largest gives that away. How many elementary schools or students and how many middle school students will be in each group? Well, that's factors again, right? Going back to all the common factors of how many are in each group. It's like that problem that was about the plates and cups, right? How many in each package, or how many packages do we need to buy? That's very similar. So for number 2, there's our answers. We need common factors and the greatest common factor. Okay? Very good. We are ready for number 3 now. Got too many papers in my way here. Number 3, lights. There is a string of holiday lights with red, gold, and blue lights. The red lights are set to blink every 12 seconds. The gold lights are set to blink every 8 seconds, and the blue lights are set to blink every 6 seconds. The lights are on an automatic timer that starts each day at 7 p.m. and stops at midnight. Part A, after how much time will all 3 lights blink at the exact same time? Okay, now this reminds me of the locker problem, right? When it said every 4 seconds, every 8 seconds, every 12 seconds, whatever they were, that is multiples, right? Because every 12 and then 24 and then 36, right? Every 12 seconds. That's a repeating pattern that keeps going until we turn the lights off, right? So that's common multiples, right? Now, after how much time will it blink at the exact same time? How much time? So that's the first time that happens, which is the least common multiple, right? How many times total will this happen in the day? Well, again, that might need finding some factors, right? Kind of like the plates and cups one, right? Yes, we needed the multiples of packages, but then we had to use factors to figure out how many packages to buy. Same thing here. We have to use those factors to help us answer part B. So there are the answers for number 3. We're breezing through these. Number 4, banners. Noah has 2 pieces of cloth. He is making square banners for students to hold during an opening day game. One piece of cloth is 72 inches wide. The other is 90 inches wide. He wants to use all the cloth, and each square banner must be of equal width and as wide as possible. So this is a hint here. As wide as possible. We want the largest possible width. So are we going to do a least common multiple if we want the biggest? Nope, we're going to use the greatest common factor, aren't we? In order to find the greatest common factor, of course, I'm going to need all the common factors, right? So that's a given there. How wide should he cut the banners? Well, that's exactly what I was just talking about, right? We're going to have to take this up and split it up into its factors because they have to be square. They have to be common. They have to be the same on each side, width and length. So the factors, the common factors are going to give us part A. How many banners will he cut? That's the greatest common factor. If we want it as wide as possible, the greatest common factor will tell us how many he can cut, won't it? So there's our answers for number 4. Again, we don't have to solve these. We just had to decide, didn't we? Alrighty, our last one, number 5. It's all about dancers. At Elena's dance recital, her performance begins with a line of 48 dancers that perform in the dark with a black light that illuminates white clothing. Ooh, I love that kind of dancing. That's super cool. All 48 dancers enter the stage in a straight line. Every third dancer wears a white headband. Every fifth dancer wears a white belt. And every 9th dancer wears a set of white gloves. Oh, that sounds cool. Okay. If Elena is the 30th dancer, what accessories will she wear? Okay. So here's our hint on this one. Every third dancer, so the 3rd dancer, the 6th dancer, the 9th dancer, those are multiples, right? Every 5th dancer, 5, 10, 15, those dancers will wear a white belt. This is common multiples, isn't it? So we definitely need multiples. And to figure out what the 30th dancer will wear, we'll just have to look at those lists of multiples and find 30 in those lists. That's very much like that problem where we had to find the 30th locker or whatever it was. Remember that? Very, very similar to this problem. We have to find, is 30 one of those multiples? Okay. Will any of the dancers wear all 3 accessories? Well, in order to wear all 3, they have to be common, right? So again, common multiples. And if so, which ones? Well, we'll have to find the least common multiple as well as other common multiples. So I think we'll need both of those so far, right? How many of each accessory will the dance teacher need to order? This one will actually need some factors, won't it? This is very similar to that first problem we did in order to answer how many packages, right? This is kind of like that. We have to figure out, okay, if we have this many, how many of those headbands will we need to buy? Or how many of those white gloves will we need to buy? So I think we're also going to need factors for this one as well. And that often happens with multiples, right? Sometimes to answer some of the questions, remember our chart back here? Sometimes when we have multiples, we also have to find some factors to answer some of the questions, right? So that actually happens quite often, okay? Awesome. Now we've moved on to number 6. I am actually not going to do the rest of this, okay? Basically, I was supposed to assign you one of those 5 problems and have you work with your group to solve it and then present it in a visual display and all of this stuff. But we're not going to worry about doing all of that. The main point of this lesson was just to identify what we have to do. And we've done that. So we're not going to waste time solving any more of those. We'll see more of those in our homework tonight. Okay? So that's the end of that activity. Now, there is one more activity in this lesson, but this is an optional activity. Okay, but it is a fun bingo game. So I highly recommend you grabbing your brothers, your sisters, your moms, your dads, your grandpas, your whoever is in your house. Print out the black line master that's in Canvas. It's going to look like this. You're going to have whoever's running the game will have this sheet. Okay, and this is what they're going to call out. Like instead of saying B5, they're going to name or call out all the numbers with 4 or more factors, right? That's going to be what people are looking for on their bingo cards, okay? So these are the bingo cards, and there's multiple pages of these, so you can have lots of people play with you. So if I were to shout out this answer, all numbers with 4 or more factors, does 24 have 4 or more factors? Well, 1, 2, 3, 4, 6, 8. Oh, I'm already over 4. So that one would get marked, wouldn't it? Again, then you're playing like bingo. You're looking for 4 in a row, up and down, sideways, or diagonally, and you're just playing bingo. So this is a really, really fun way to review all of this stuff about factors and multiples and different things like that. It's a great way to practice that. So follow these instructions, print out the cards and cut them apart. Assign somebody to be the runner of the game because they're the only people that sees this page, right? Everybody else just gets a bingo card. And have fun. Play this bingo. It'll be a great review, not only for this lesson, but for the test, which is tomorrow. That's right. This is our last lesson of the unit. So tomorrow is our Unit 7 test. Make sure you read through the summary pages. They're really good for this one. And then you'll be ready for the practice problems tonight, which I will do with you in just a few minutes. But again, remember, the test is tomorrow. So let's make sure that we practice, that we study, and that we're doing everything we need to do so that we're 100% ready for tomorrow's test. It's time now to jump into your homework problems. I know you will work hard on these and get these done. And I know that, as always,
do your best, because you deserve your best.
Alrighty, we've just finished up working on our practice problems and doing our very, very best, right? So now let's go through these and make sure we did them correctly. In number 1 practice problem, it says, Mai, Claire, and Noah are making signs to advertise the school dance. It takes Mai 6 minutes to complete a sign. It takes Claire 8 minutes to complete a sign, and it takes Noah 5 minutes to complete a sign. They keep working at the same rate for a half hour. Will Mai and Claire complete a sign at the same time? Explain your reasoning. Well, in order to know whether or not Mai and Claire will complete a sign at the same time, I'm going to need to find the common multiples, right? Because every 6 minutes, 6, 12, 20, 18, right? Mai will finish a sign. And every 8 minutes, Claire will. So 8, 16, 24, right? And every 5 minutes, Noah will. 5, 10, 15. So let's start this problem by finding the common multiples up to, when can we stop? We can stop at a half an hour. So we can stop at 30 minutes, can't we? So let's do Mai. Yeah, I think we'll have room over here. I was going to move up top, but I think we'll have room. We have Mai, Claire, and Noah. Okay, so Mai is every 6 minutes. So 6, 12, 18, 24, 30. There's my 30-minute mark, so I can stop, okay? For Claire, it takes Claire 8 minutes. So 8, 16, 24, 32. That's too big, so we can actually stop at 24. For Noah, he takes 5 minutes. So his multiples are 5, 10, 15, 20, 25, and 30. Once again, I can stop because we're stopping at a half an hour. Okay. So will Mai and Claire complete a sign at the same time? So if we are only comparing Mai and Claire, do they have a common multiple? It looks like they do at 24. There's a common multiple at 24. Yes. After 24 minutes. Because, explain your reasoning, 24 is a common multiple of 6 and 8. And I wrote them backwards, 8 and 6, but either way is fine. Okay? So, part B, will Mai and Noah complete a sign at the same time? Explain your reasoning. So now we're comparing Mai and Noah. So top row and bottom row. Do you see any common numbers between Mai and Noah? I do, but not until 30, right? Do you see that? I don't see anything until 30 minutes, but at the very end, they will finish one at the exact same time, won't they? So Mai and Noah will complete the sign, yes, after 30 minutes. And the reasoning is the same. 30 is a common multiple of, and they were 6 and 5. Okay? Very good. Part C. Will Claire and Noah complete a sign at the same time? So now we're comparing Claire and Noah. What do you think? Are they going to finish a sign at the exact same time? I don't see any. I mean, none of these are multiples of 5, are they? So no, I don't think nope. The answer to C is absolutely no. They don't have common multiples. Okay, So nope, they will never finish a sign at exactly the same time. Will all 3 students complete a sign at the same time? Explain your reasoning. So is there a common multiple between all 3 people? Well, the fact that we answered no to Claire and Noah means no, none of them will finish at the same time. And we can double check. Is there a common multiple between all 3 lists? I don't see a single one. And I was expecting that when I got a no there. So this is no. Again, there are no common multiples among all 3 kids. Right? Nope, they'll never do it all at the exact same time. Okay? Very, very good. That's number 1. Number 2, Diego has 48 chocolate chip cookies, 64 vanilla cookies, and 100 raisin cookies for a bake sale. He wants to make bags that have all 3 cookie flavors and the same number of each flavor per bag. How many bags can he make without having any cookies left over? Okay, so we don't want to have any cookies left over. We want to use the cookies we have, so we're limited on our supplies. What does that sound like? That is screaming GCF to me, right? So let's find the greatest common factors, or all the common factors of 48, 64, and 100. Let's just do that. I think we'll have room in our space right here. 48, 64, and 100. All right, the factors of 48 are 1 and 48, 2 and 24, 3 and I think it's 16, 4 and 12, and 6 and 8. Oh, I need a comma in there. There they are for 48. For 64, we have 1 and 64, 2 and 32, 3 doesn't go in, 4, and I think it's 16, isn't it? I better check that. 64 times 4. What am I doing? Not 64 times 4, 16 times 4. That's 24, 4. Yeah, that's 64. Okay, so I was right. 4 times 16. 5 doesn't go in. 6 doesn't go in. 7, 8. 8 does. 8 times itself. 8 times 8. So 8, I'm just going to move these over. 16, 32, and 64. Then I can erase the repeats here. All right. 100. 1 and 100. 2 and 50. 3 doesn't go in. 4 does. 4 times 25. 5, oh, I'm running out of room. I better give myself more room real quick. We know that 5 will go in. 5 times 20. 6 does not. 7 does not. 8 does not. 9 does not. But 10 does. 10 times 10. Now I can go backwards. 5 times 20. 4 times 25. 2 times 50. And 1 times 100. There. Now we've got our factors. Now we need to answer this question. How many bags can he make without having any cookies left over? Let's find our common. He can make 1 bag. He can make 2 bags. He can make... Any more? That might be it. Oh, 4. I skipped right over 4. You probably saw it before I did. 4 is common. So he can make 4, right? Well, he can make 1 bag, 2 bags, not 3 bags. But he can make 4. Because it didn't say what's the largest number of bags. It says how many bags can he make. So he can make 1 bag, he can make 2 bags, or he can make 4 bags. Okay? Find another solution to this problem. Oh, we did find all the solutions to this problem, right? So yeah, we can do 4 bags, we can do 2 bags or 1 bag. Okay? So we've actually done both of those parts already. Okay? Number 3, find the product of 12 and 8. Well, product just means multiply. So 12 times 8, in fact, we could use our multiplication chart if you don't know what that is, but I already know that 12 times 8 equals 72. Okay, find the greatest common factor of 12 and 8. Okay, so in order to do that, I have to list these factors. Okay, so for the factors of 12 and 8, let's do those. 12, the factors are 1, 2, 3, 4, 6, and 12. When you get as old as I am, you start memorizing the factors. The factors of 8 are 1, 2, 4, and 8. So what is the greatest common factor of 12 and 8? It looks to me like it is 4. The least common multiple of 12 and 8. Well, okay, here we go. Multiples of 12 are 12, 24, 36, 48. So let's see if I have to keep going. And of 8. 8, 16, 24. Oh, there's this common one. So I could actually stop at that one. 24 is the least common multiple. Okay? Find the product of the greatest common factor and the least common multiple of 12 and 8. So we have to now multiply my greatest common factor of 4 times my least common multiple of 24. Well, 4 times 24 is 9. Whoa, what am I writing? I wasn't even thinking that number. 96 is my product. What do you notice about your answers to questions 1 and 4? Or I think they mean A and B. Oh my gosh. I have the answer to A actually wrong, and I didn't even notice it until I got to answer 4, because guess what? They're supposed to be 12 times 8. I totally did that wrong. I only did 12 times 6. 12 times 8 is 96, right? So what do we notice about our answers? They are the same. Choose 2 other numbers and repeat steps 1 through 5. Do you get the same results? Now I'm going to let you do that. And if you did that, awesome. And what you will find is absolutely yes. That's why I was actually thinking, oh crap, I did something wrong. Because yes, every time that actually will work. It's kind of a cool thing that the product of 2 numbers and the product of their GCF and their LCM will always be the same answer. So if you get one of those answers, you can find the other one by dividing to go backwards. Oh my goodness, what a cool trick. That is super fun. I love that they pointed that out in this homework assignment. Let's move on to number 4. Oh, I forgot. In this assignment, you do not have to do problem number 4. Did you notice that on Canvas? Okay. Do not do number 4. Okay, because this is from the lessons that we skipped. Okay. So don't do number 4. If you already tried it, you were probably pretty confused because we did skip that lesson. So don't worry about number 4. Number 5, find the value of each expression mentally. Oh, we got to do as much of this in our heads as we can. Well, for part A of number 5, I noticed that there's a difference, a subtraction of 2 products. And notice I have 1/2 in both products. So what if I pull that outside parentheses and do 37 minus 7 on the inside? Do you remember this? This is the distribution property. Now I can solve this. 37 minus 7 is 30. 30 times 1/2, or 30 cut in half, is 15. Done. I didn't have to do a whole bunch of nasty math, did I? Very, very good. How about part B? Can we find the same process here? I think we can. There's a sum of 2 products, and there's a common factor in our 2 products. Let's pull that outside. We have 40 plus 60 on the inside. 40 plus 60 is 100. 100 times 3.5. Well, timesing by 100 just moves the decimal point twice. So this becomes 350. Done. Wow, that's awesome. Now, part C. This one is just one of those mental math tricks. 999 is really close to 1,000, right? So if I do that math instead, what do I have left over? Well, I have 1,000, whoops. I have, oh gosh, I'm not writing very good. In fact, I'm going to erase this. I have 5 times 1,000 minus 1, right? Because 1,000 minus 1 is 999, and multiplying that by 5 gives me basically the exact same problem, right? But let's separate this out like these problems. This is actually 5 times 1,000 minus 5 times 1. In this case, doing it the long way is actually easier because 5 times 1,000 is 5,000 minus 5 times 1 is 5, and 5,000 minus 5 is 4,995, and that's my answer. So we can go both directions to help us mentally solve problems like this. I love that strategy. It's super handy to help us do math in our heads instead of the long and arduous long multiplication, isn't it? Good job, good job. Guess what, ladies and gentlemen? You just finished your last homework for Unit 7. Hallelujah. Unit 7 is now done. We are ready for our last Check Your Understanding quiz of Unit 7. So make sure you dive into Canvas and take that last Check Your Understanding quiz. And then whatever other time you have today and tomorrow, you'll need to spend studying, okay? I highly recommend you look at the summary pages, look back over your practice problems and the lesson activities, study, maybe go back over those Check Your Understanding quizzes, maybe retake some of those that you didn't do so well. That's a great way to study because then not only can you get a better score on those quizzes, but you'll refresh those problems in your mind because guess what? All of those Check Your Understanding quizzes, those questions are very, very, very similar to what you're going to see on the Unit 7 test. That's why I chose those questions, because they're so similar to the test. So if you can do the Check Your Understanding quizzes, you'll be just fine on the test. You can guarantee that, okay? So study hard, get all your work done, and then tomorrow we are going to take Unit 7 test. I know you'll do awesome because I know that you will
do your best because you deserve your best.